Okay, we are on chapter 3 we got into last time. And in chapter 3, we are talking about matter, and we got into kind of the three states of matter. Again, remember, we do have the solid state of matter, where everybody is usually sort of piled in there pretty tight to one another. Not a lot of room for movement, not a lot of energy happening in the solid state. Again, that's why solids are pretty rigid. They have fixed sort of shapes. We also talked about the liquid state. And again, a reminder, in the liquid state, we still have people sort of fairly close to one another. There is a little bit more room for movement. Again, that's why liquids are more fluid. They also have a little bit more energy, which allows them to sort of pass one another. And then we have the gas state. And in the gas state, everybody has completely sort of broken apart from one another. They're flying around. They have probably the most energy of everybody. As we'll talk about when we get into the gas chapter, the collisions that occur as they are flying around with all that energy is what causes pressure that we associate with gases. We also talked about sort of the changes of state. And again, as you go from solid to liquid, that's the process of melting. Going backwards, liquid to solid, that's the process of freezing. Going from liquid to gas, that's evaporation or vaporization. Going from gas back to liquid, that is condensation. Going from solid, skipping the liquid phase directly to the gas phase, that is sublimation. And gas skipping the liquid phase back to solid is deposition. So we also talked about sort of the association of energy with these processes. Remember, as we go from solid to liquid to gas, those are all processes that require energy to basically be put in. So energy is absorbed in this case. And as we talked about, and we'll talk about in the next chapter, that is what is known as being an endothermic process. Going in the opposite direction, if we went from gas to liquid to solid, they basically are going to release their energy. And when they do that, for example, the gas molecules won't be flying around with as much energy. So when they do collide, they no longer perhaps have enough energy to completely kind of escape each other, and they kind of stick together, if you want to think about it that way, and they fall into the liquid phase. As you continue to remove the energy, for example, from the liquid phase, again, they lack that energy to start passing one another, and they just sort of fall into place into the solid state as they release that. Those are what are known as exothermic processes. And remember, as we talked about, melting and freezing, and also evaporation and condensation occur at the same temperature. That is usually the boiling point of a substance where we have that transition. This is usually the melting point, freezing point of a substance when we do that. Remember, at exactly those temperatures, so we talked about water in general, which is 0 degrees Celsius for water is where it freezes and also melts. And at exactly 0 degrees Celsius, you do have both phases happening at the same time. So you have like ice crystals, like we talked about, some solid, some liquid. Not until you get above 0 that you really go into the liquid phase. Not until you're below 0 that you really do sort of stay into the solid phase. And the same thing with the boiling point for water, that's 100 degrees Celsius. And again, exactly 100 degrees, you really do have both things happening. You have liquid and you also have steam or gas in the case of water. And it's not until you really get above that boiling point or below that boiling point that you fully do sort of transition from one phase basically to the next. Any questions on any of that stuff we talked about? Clearly, also, we talked about matters, anything basically that occupies space and has mass, which is pretty much most things along the way. All right, so continuing on this chapter here, the next thing we're going to talk about is physical and chemical properties and changes. And the first thing we're going to talk about is a physical property. And a physical property is a property that can be observed without changing the composition or identity of a substance. Typical physical properties are odor, color, volume. Probably the most common physical property we come across in matter is these different states, solid, liquid, and gas. And density, melting points, and boiling points are all examples of physical properties. For example, you can measure the melting point of ice by heating a block of ice, recording the temperature at which it will be converted into water or liquid water. But since it only differs in appearance, it is just a physical change. And that's important for a physical change. And the importance of a physical change is basically what you start with and what you end with are fundamentally the same thing. So, for example, most common physical changes are what we just talked about here: solid, liquid, gas. All those transitions, evaporation, condensation, melting, freezing, those are all physical changes. So, as the example here states, if you had an ice cube is H2O, it is fundamentally water. When you heat that in, it melts to liquid water. It is still H2O. It just looks different, obviously, than the solid. And even the one that confuses or people get wrong all the time is you heat up water to make like pasta and you have all that steam. Steam is also just water. So all three of those things are fundamentally the exact same thing. They're all H2O. They're just different sort of physical our shapes of them, our phases of them. In the ice is more solid. In the liquid, obviously, is liquid, and obviously in the gas or steam, it is our gas phase. But because it is H2O in all those cases, it is a physical change. This is not a chemical change. So one of the kind of hallmarks of a physical change, for example, is in a lot of cases, you can get back, for example, the original thing by doing some type of physical change to it. So, for example, if you took that liquid water, like we talked about maybe last time, and you froze it, which is a physical change, you would get the ice back, right? And obviously, if you take the ice cube out, it'll melt back into liquid water, so you could kind of go back and forth. If you took a piece of paper and tore it into a bunch of different pieces, right? It is still fundamentally still paper, just in a lot of different pieces. There is no chemical change that occurred in that case. Again, technically, you could tape it back together, glue it back together. It'll sort of look like the original piece of paper. So a physical change, the importance is what you start with and what you end with are still fundamentally the exact same thing. And that is different than, for example, what we see with a chemical change or a chemical property. And again, as we talked about with the ice, we could obviously freeze our liquid water back and recover our original ice in its sort of regular shape. So melting points of a substance are physical properties, freezing points as well. Now, a chemical property is really the ability of something to go through a chemical reaction or be resistant to chemical reaction or chemical change. So when we talk about a chemical change is what you start with and end with are different things. Basically, something new has been made as a result of a chemical reaction occurring. So chemical changes are oftentimes called chemical reactions. So for example, we took that example of the paper a second ago. If instead of tearing the paper, you set the paper on fire, it's now going to change it to a lot of new different things. And that is definitely a chemical change that you cannot get back. The rusting of steel in our cars or just metal in general. For rust, you need iron. You need a little bit of water, some moisture, and you need some oxygen gas. And basically, before rust occurs, the iron is by itself. After rust occurs, these two guys get chemically sort of bonded together and make a little iron 3 oxide, which is rust. Those guys are now chemically united together. You do whatever you want with rust, for example. You can put it in the freezer. You could heat it up. You will not get the metal back, and you will not get the oxygen back as well. Same thing, for example, if you took some hydrogen gas and some oxygen gas and you put it together to make some water, when those guys chemically unite, we'll balance it like we're chemistry here. You'll make that water, and it's at that point you can do whatever you want to that water, sort of physically, like we just talked about a second ago. You could heat it up, right, and start to boil it, but it makes steam. That's still water, right? Physical change. You could put it in the freezer. You're not going to get the hydrogen gas and oxygen gas back. That's really good. Otherwise, when you do go try to make the pasta for dinner, you won't get there because you're making hydrogen gas and oxygen gas, and it would explode perhaps, and it wouldn't be such a great situation. But the only way, for example, to get back the hydrogen gas and oxygen gas is you actually have to do a chemical change to it. And that would be if you took an electrical current, for example, and you ran it through water, you would be able to get the hydrogen gas and oxygen gas back. And that would be, though, a chemical change to do that. So you're actually breaking apart that compound into its elements as a physical change. The properties of hydrogen gas and oxygen gas are very, very different than obviously the properties of water as well. And again, you made two new things in this case. So the deal is with a chemical change, what we're looking for is whatever we start with and whatever we end with, they do have to be fundamentally different things, and you can't get it back by any type of physical means. And again, a chemical property is the ability of something to go through a chemical reaction or even resist a chemical reaction. So as I mentioned there, hydrogen gas and oxygen gas will form water. Once we make that new substance, it is not going to go back. You can't get those things back by any type of physical means without doing any type of chemical change to it. Hard-boiled egg as well. Again, when we hit it to 100 degrees, the yolk changes appearance, and also its chemical makeup also changes. And obviously when we eat something, any type of food, right, we got enzymes and stuff in our body that breaks it down into a bunch of different things and changes it from what it was to a lot of different things as you need it for, obviously, your fuel and so forth. So the key here, physical change, involves one or more physical properties, and we have no change in fundamentally what something is. If you took a peanut and you crushed it, it is a physical change. It's just a small bunch of peanuts, but it's still fundamentally still peanuts. If you have a shirt and you iron the wrinkles out of it, still a shirt, right? It's fundamentally still the same, just looks different and stuff like that, right? You took a shirt and you painted it with some paint, right? It's still a shirt overall, it just looks green now, right? Because you threw some paint on it. And that again is different than a chemical change. What you start with and what you end with, definitely fundamentally different things. Again, most common sort of physical changes we see a lot is those changes of state, going from solid to liquid to gas and back and forth. For example, silver tarnishing. Again, silver with a little sulfide there mixed together makes it start to tarnish and really oxidize. So let's talk a little about elements and compounds. Elements is a substance that cannot be basically broken down into any further back. The basic unit of an element, as we'll talk about in chapter 4, I think, is an atom. Atoms have protons, neutrons, and electrons. So the basic representation of elements are atoms. Elements are as far back as you could go. The periodic table up there, right, has all of the elements that we have going on. You could think of elements like the alphabet. It is basically the basis of everything. The different combinations that you put together, the different amounts of elements that come together give you different sort of compounds. that have different sort of properties. So just like in the alphabet, right, we could put a bunch of different letters together, we get a bunch of different words to have different meanings, and that's sort of the same idea here. Now, when you look at the periodic table and you look at all those elements, most of those elements are what are known as being monoatomic. Monoatomic means one atom. That is how they come. So if I had a piece of iron metal, that would be just Fe. By the way, it would be a solid. And it would not have a charge. And that's something people misunderstand a lot, and we'll talk about it when we get there. But in general, if you take anything off the periodic table by itself and it's not combined with anything else, it does not have a charge. So things only get charges when they start combining with other things, and we'll talk about it. But when metals and nonmetals come together, that is when we get charges. But again, if you had a piece of copper, just going to be Cu for copper. The S means it's a solid piece of metal. So this here is a solid. Same thing here. There are certain elements, though, that are what are referred to as being diatomic molecules. So we'll start with the first part there. Diatomic means they come as two atoms together. So the guys that come as two atoms together that are still elements, hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodide. These sort of seven, I think there is, seven guys here, these are all elements. These are all elements, and this is naturally how they come as twos. So if you had hydrogen, which is hydrogen gas, it is basically two hydrogen atoms bonded to each other. If you have oxygen, which is oxygen gas, it is two oxygen atoms bound together, sharing electrons, flying around. If you had nitrogen, same deal, two nitrogens bound to each other, and so forth all the way down there. These guys are what are referred to as molecules, and sometimes people have a hard time with molecules, and as we'll see in a second, compounds. Let's start with molecules. Molecules is just a simple definition of two or more atoms together. That's basically all you need for something to be a molecule. So basically, two or more atoms together. So if you have two or more atoms together, that is all you need for something to be considered a molecule. And that is why we consider each of these guys here to be molecules, because they are, as you can see, two atoms of hydrogen, two atoms of oxygen, two atoms of nitrogen that are together. They are also considered elements because the only atoms there are the same element. So for H2, they're both hydrogens, so they are still considered elements because there's no other element atom involved. Oxygen, obviously, two atoms of oxygen present, so they are considered elements, and they are considered molecules as well. Now, if we look at something like a compound, and oftentimes people compound and molecule, and we'll throw element in there as well, have a hard time sort of distinguishing some of the differences between them, but most of the time it's these two that give people sort of a hard time. So what is the difference between these two? As we just talked about a second ago, a molecule is a basic definition of two or more atoms that are together and really bound together. Now, a compound is two or more atoms of different elements. So in order for something to be a compound, you need to have atoms of different elements involved. For a molecule, you do not, as we just saw there a second ago. We could have two hydrogens, which is still a molecule, but it's an element. We could have two nitrogens, which again is a molecule. Neither one of those things, the hydrogen or the nitrogen, is a compound. And that is because it only contains oxygen or nitrogen or hydrogen in those. Now, if you took something like water, which is H2O, H2O has definitely two or more atoms, right, together, two hydrogens and one oxygen's involved, which means it is a molecule. Now, it also has atoms of two or more different elements, which means it is also a compound as well. Water, though, is not an element because it contains hydrogen and oxygen together, so it is not an element. Now, if you took the example we did a second ago, like hydrogen or H2, H2 is a molecule because, again, it's got two or more atoms together. It is not a compound because it only contains hydrogen, but it is an element because it contains only hydrogen. So an element can be a molecule, but it cannot be a compound because it would not be an element at that point because it has to be the same element to be involved to remain an element. A molecule can also be a compound, but if it's a compound, it cannot be an element because in order to be a compound, it has to have two or more different elements involved. So that is the difference between it. So for example, if I take CO2, is that a molecule? It is a molecule because it's basically one, two, three atoms together, right? So that's the basic definition of a molecule. Is it a compound? It is a compound, right? So this is a compound because, again, it has two different elements involved. It is a molecule because it's got two or more atoms involved. It is not an element, though, right? Again, because it has carbon and oxygen involved. So this is not an element. So sometimes people are not sure about the difference between these two. The way you should think about it is a molecule is really just like a basic definition of all you have to do to get to a molecule is you just need two or more atoms. It could be the same elements, could be different elements, but that's all you need for it to be a molecule. In order for it to be a compound, you need the additional thing of two or more atoms that has two or more elements involved for it to be a compound. And obviously to be an element, it can only have atoms of the same element involved. Any questions on that difference there? Okay. Now, compounds can be broken up into their elements by chemical means. So as an example, what we were talking about earlier, you could take water, you could run an electrical current through it, and you will get back the hydrogen gas, and I think you'll do it actually in a lab coming up. You'll get the hydrogen gas and the oxygen gas, just a 9-volt battery and a little bit of acidic water will let you do that. And again, we can go from a compound here to its elements. But this is as far as we could go. We can't go back any further. We cannot break these guys down any further. That is basically the end of the line at that point. So a compound always, like I said, contains atoms of different elements. Now the property of compounds are usually very different, for example, than the elements that make it up. So for example, if we took some sodium metal and we added some chlorine gas to it to make a little sodium chloride, or salt, if you will. Now, sodium is a very soft metal. Chlorine gas is a toxic green gas. But through the miracle of chemistry, when they come together to make a compound which contains now sodium atoms and chlorine atoms, right? You get salt, which won't kill you when you put it on your fries, right? So very, very different properties, usually the compounds from the properties of the elements. Even water, right? Water is pretty stable, pretty not too bad, right? Not bad things happen. But hydrogen gas and oxygen gas are, flammable and stuff like that, right? So very, very different properties than obviously the water compound that they both make up when they come together. Any questions on that there? The next thing we're going to talk about is pure substances and mixtures. So a pure substance is basically anything that you have that is just that one thing by itself. So for example, if I took some water, that is a pure substance. If that's all I have there, it's just some water in a beaker or whatever it may be, that's considered a pure substance. If I had some sodium chloride or some salt, basically, right? And I had that by itself, that is considered a pure substance as well. Now, if you take two or more pure substances and you put them together, you get what is known as a mixture. So if you mix together two or more pure substances, you will get a mixture. And in this case, we will actually get NaCl in the aqueous state. Aqueous state is basically a solution. You basically will get some salt water here. Salt water is a mixture of two pure substances, water and salt, coming together to make that salt water. In this particular case, if you look at salt water, right, it just looks at water. You can't really see the salt in a lot of cases. The salt will dissolve in the water part and it's no longer visible to you. The key, though, with a mixture, and one of the really important things to remember about mixtures, is even though they are mixed, those substances still retain their identity. So even though you can't see the salt, it is still there. Yeah, the salt is still there. The water is there, and they both retain their identity, even though it looks like that. Which means what you start with here and what you end with when you make a mixture is really the same thing. It just may look different to you. Is that a physical change or a chemical change? It's a physical change, yeah? So when you make a mixture, it's actually a physical change, even though you can't see the salt anymore and it disappears. We'll talk about why it disappears and how it disappears in a bit, but it is still there and you could get it back if you wanted to, and that is a physical change that occurs. So sometimes people think a mixture is a chemical change, especially in this type of situation where you have the salt, then it's gone, and you think, well, oh, something must have happened chemically to make it disappear, but it's actually a physical change that's occurring. Now, mixtures could be one of two types of mixtures. It could be a homogeneous mixture, and in a homogeneous mixture, everything looks the same throughout. So in a homogeneous mixture, everything will look the same throughout. Sometimes people think of it as like you got one layer. So the saltwater example that we just did a second ago, that is an example of a homogeneous mixture. Once again, if you looked at some salt water, if you went to the beach and you grabbed some water out of the ocean and nothing else floating around in the ocean, just the water, it will just look like water to you, right? But if you ever tasted it, which you might have if you went swimming in the ocean before, it tastes quite salty, right? And there's a lot of salt and other things dissolved in there. And it looks the same throughout. So if you took some sugar, a spoonful of sugar, and you put it into water, the sugar would dissolve, but it would just look like water to you until you tasted it, right? And then you go, oh, there's like some sugar in this thing, right? And again, those are homogeneous mixtures. The other type of mixture is a heterogeneous mixture. In a heterogeneous mixture, you actually see different layers. So for example, if you took like water and you added some sand to it, which you might do in a bit, when you do that, you can mix that all day. You will still see the sand, right? The sand is never going to dissolve. You will see the sand as a part of it. Or if you put some metal pieces into water, you can mix that all day, and those metal pieces are not going to dissolve in the water or react with the water as long as they're not water reactive metals. And they will stay there and be there, and you'll be able to see it. So in a heterogeneous mixture, you're able to see these different layers. So homogeneous, everything looks the same. Heterogeneous, you see different layers, it's sometimes referred to, or phases. You're able to physically sort of see the difference there for it to be a heterogeneous mixture. Any questions on the difference between them? So homogeneous looks the same. Heterogeneous, you see those different layers. Now, regardless of the type of mixture that you have, be it a homogeneous mixture like the salt water, be it the sand and the water there that you have, which is a heterogeneous mixture, you can separate out those mixtures and get back the pure components. And sometimes you get them back into their original forms. And again, this is why we consider making a mixture a physical change, because you could do a physical process like filtration, like heating it up, to separate out the different parts of it. How would we do something like that? Well, let's just take the one heterogeneous example here, where we got some sand plus water here. So sand and water, heterogeneous. A very simple way and good way to separate out a solid from a liquid is to do the process known as filtration. And in the process of filtration, use something like a funnel. Put a piece of like filter paper here in your funnel. And when you go and pour your mixture of sand and water through the filter paper, what's going to happen is your sand, I'll color it blue here, your sand is going to get caught up on the filter paper. Your liquid water will be no problem. It's going to drip through the bottom of it. Although on a piece of filter paper, you may not be able to see it. There's holes. And those holes are big enough to let certain size molecules pass through, like water, and small enough to not let bigger particles like sand pass through. We are actually separating these guys by physical means, size, right? Physical property. So by size, we could actually separate these guys by doing a filtration. And if I let this come through, I will now have my water component of my mixture. And up here, I will have my sand component. I could take my filter paper, let it dry out, and now I got dry sand, just like I had when I started with. And again, through a physical process of filtration, we're able to separate out this physical change that occurred and get back both the sand and the water in its original form. Any questions on that? Now, if you had something like the other type of mixture that we talked about, which is the salt water, right? And in this case, this is a homogeneous mixture. And again, to you, it may appear like, wait, the salt's gone. It's just water. Something chemically had to happen in this. And again, it's not. It is a physical process. So if I set up an apparatus, we'll have a much prettier picture of this apparatus in a second here. But sort of a closed system. And if I put my salt water on one side, and the connecting tube here is kept really cold between the two. And if I take my salt water and I decide, well, I want to separate it out and get both parts back, I put my wonderfully drawn Bunsen burner, also known as a triangle on a line there, and I start to heat this salt water. What's going to happen to the water part once you start heating water? It starts to evaporate, right? So the water here is going to start to evaporate. It's going to make steam, right? Which is the gas version of water. Because this is a closed container, it's got nowhere to go. So this gas version of water is now going to go through this really, really cold tube here. And when you have gas and it goes through cold, you remove energy and it goes back through condensation and becomes liquid water over here, yeah? And if you continue to heat this thing and continue to heat this thing, you will send all your water that will be steam and then cooled back down and evaporated back down to the other side. And if you continue to heat this thing until you evaporate off all of the water on this side, you will be left with just some salt over here, which I'll make as these little dots here. And here, by this simple process of heating it, we now have on the right-hand side my water, which was the original component. and I have my salt on the left-hand side, right? Also a component. And we have now successfully separated out this mixture where before we see it, or did it, or heated it, we couldn't even see the salt anywhere, right? It just like was not there, and now it's back. And this is how we know, again, it's a physical change it's going to do here. You might have done something similar to this in an earlier, not sure if you did or not, but maybe. Or you will soon. But for example, we could sometimes use in the lab an evaporating dish. An evaporating dish works the same way, except for the fact that we're not trapping the water when we do it. Yeah? So when we heat in an evaporating dish, because it's an open system, when that water starts to evaporate, it just gets lost in the air, right? And we're not saving it. But if we wanted to save it, we could do this type of process. This is known as distillation, which is a really good way to separate out homogeneous mixtures. What are we using here to separate out these mixtures, this homogeneous mixture? We're using boiling point, right? A physical property. All we have to do is get that mixture to 100 degrees Celsius, and that's enough for the water to boil and change phases, right? You could continue to heat that as much as you want. Salts and ionic compound, as we're talking about, is held together super strong, which means you could heat the heck out of that, and that salt will first start to melt before it ever go into the gas phase, and it'll never go into the gas phase. So by using differences in the boiling point of the salt and the water, which are physical properties, we're able to separate out this obviously physical mixture by using those differences to separate it out. Any questions on that? Why is this actually happening, and why does it disappear when you dissolve salt? We'll talk about it, but water is actually what is known as a polar molecule. And basically, water has two sides. It has a side that is negatively charged, which is the oxygen side of water. It has a positive side, which is actually the hydrogen side is more positive. And in chemistry, a very important principle is, much like in life, opposites attract, right? So something that's positive and negative are going to be attracted to each other. Like a positive and negative person, right? They are attracted to each other. Two positive people, very annoying to be around, perhaps, right? They repel each other. Two negative people, also, right? Don't want to be around each other. They also repel each other. So things that have similar charges don't want to be around each other. So negative, negative, don't want to be near each other. Positive and positive don't want to be near each other. But opposites do attract. So when you take something like sodium chloride, which is a salt, it actually, when it goes for a swim, breaks apart into ions. And what you really have is a sodium ion there, and you have a chloride ion, and that is the sodium chloride or salt part of your mixture here. And what happens is the oxygen side of water is actually attracted to the sodium ion, which is positively charged. And what happens is a bunch of water molecules basically surround the sodium ion. It also, the water is attracted to the chloride, which is negatively charged, but it's actually attracted through the hydrogens, which are positively charged, opposite side. And the hydrogen side of water actually will surround the negative ion, in this case of chloride. And that does two things. That basically keeps those two positive ions, the sodium ion and the chloride ion, the positive ion there and the negative ion, away from each other. That's also how it dissolves, because there is so many water molecules that you no longer can visually see the sodium or chloride in that solution, because it's just surrounded in the water matrix. It disappears. It's not visible to you in your naked eye. It only becomes visible again when we heat it, because once we heat this, basically what's going to happen is all those water molecules, they're just going to evaporate away. And now there is nothing to prevent these two guys from coming back together. And when they come back together, that is when they make the solid sodium chloride that is left there in the beaker or whatever you're heating it in. So the reason it disappears, and perhaps why people sometimes think it's a chemical change, is it actually just visually disappears from us, because there's so many water molecules surrounding it, you can't see it anymore. But it's actually still there in its original form. Once you heat it, get rid of those water molecules, nothing's going to stop that positive and negative guy from coming back together. And that's why we see it reappear after you evaporate off the water. Any questions on that there? So again, these are two very common methods of separating mixtures: distillation and filtration. And again, they're really all just using physical properties as a way to separate out things and size exclusion. Here's a much prettier picture of distillation apparatus. Probably cost more than what I built, I suppose, on my picture. But same idea here. We have our salt water. As we continue to heat it, we're going to evaporate. That steam has nowhere to go but to basically be condensating back over here on the other side. As you continue to do that, you will be left with your two components here. And again, our physical change. Any questions on types of mixtures or ways to separate them out? So again, homogeneous looks the same. You should only see kind of like one layer. You shouldn't be able to see the different components of the mixture. Heterogeneous, you will definitely see different layers. The best heterogeneous mixture, right, is obviously a chocolate chip cookie, right? You can see all the chocolate chips in it, right? So you can definitely see there's a lot of stuff mixed together in it as you do it. And any questions on that there? All right, that is chapter 3. I told you it was a short chapter. Going ahead a few chapters, so we're going to talk about some things to fill in some of the blanks that might occur in this chapter because, you know, when they wrote the book, they probably assumed maybe go chapter, you know, 3, 4, 5, 6, 7, 8, 9 in a row. And in those chapters, they talk about reactions and chemical equations. So we'll touch upon some of that stuff to help you tie it together here in what's going on in this chapter. But just keep that in mind. Obviously, some of the stuff is from previous chapters that they probably assumed that you maybe did. All right, so when we talk about energy, and really what we're talking about here is what's sometimes referred to as thermodynamics. And one of the first laws of thermodynamics, which we'll talk more about in Chem 1A when you take it, is the conservation of energy. And when we talk about this sort of idea of thermodynamics, we'll talk about more of it in 1B as well. There's two types of things that we deal with usually. And what we deal with is the system and the surroundings. So for example, we have the system, and the system really can be, in our purposes here, anything that you're working with. So if you're doing an experiment in your test tube, your system is your test tube. If you're doing your experiment in a beaker, then the beaker is your test tube. You know, whatever it may be, or your beaker is your system, not your test tube. Your beaker is your system. And everything outside of that is considered the surroundings. And in the context of sort of energy, as we'll talk about, we are going to talk about really the flow of energy, perhaps from the system to the surroundings, or the surroundings to the system, right? And those are your kind of two options that could occur. Now, when we talk about systems, there's three types of systems that we come across. One is an open system. And in an open system, you can exchange mass and energy. So if you think about just a beaker that has no top on it, you could go in there and take out, you know, mass. You could take out the liquid that's in there or whatever may be in there, solid that might be in there. And it could also transfer energy with the surroundings. A closed system, you could transfer energy but not mass. So if you take something like a flask and put a stopper or a lid on something, you can't take out anything, right? It's trapped in there, the matter. But you can still exchange mass or energy. And in an isolated system, there's really no transfer of mass or energy occurring. And here's a picture of those. Open sort of system, you can take out what's inside. Also heat and energy sort of transfer in and out. You put like a stopper on top there. That's going to prevent any of these things from leaving the container. So the mass can no longer leave, but you can still have that energy or heat being transferred. And in an isolated system, you got basically no effect to the surroundings happening. You can't take anything out in terms of mass. You also can't have heat transfer in terms of energy moving and stuff. I would say in most cases, we deal a lot with open systems and sometimes closed systems. So sometimes we put lids on things when we do experiments. Sometimes we just leave it open. That's most of the time that what we deal with. A lot of times though, sometimes people use more of an isolated system, as we'll talk about a little bit later on. For example, to figure out you know, how many calories there are, for example, in your food or something like that. They sometimes use a really isolated system where they could just measure what's coming out from, say, energy coming from your food. So let's talk a little about energy. Energy is the capacity to do work are change to do work or to produce some type of change. I would say some common units, as we'll talk about in terms of energy, are joules, are kilojoules, are common units, and calories are kilocalories, are common units. And by the way, this calorie here is a lowercase c, and there is a different calorie that you sometimes see, which is a capital calorie, if you will. And that is sometimes referred to as a nutritional calorie. And a nutritional calorie, for example, is actually 1,000 of the little calories, dramatically drawn there with a lowercase c, are 1 kilocalorie. So most of the time, I'll be honest with you, most of the time in the chemistry here, joules and kilojoules is pretty much what you're rolling with. But calories, lowercase calories does pop up a lot. But nutritional calories are usually with the capital C. So there actually is a difference if you write a capital C for calories versus a lowercase c, about 1,000-fold difference. So you just want to be careful on that. Now, there is different types of energy. There is chemical energy and energy, for example, that's stored in the structural units of chemical substances. For example, bonds, right? If we have a bond between somebody that's sharing electrons, if I want to break a bond, I actually have to put energy in to do that. So if you think about a bond, they're together. If you put energy in, everybody gains energy and they wiggle away from each other, right? They have enough energy basically to break apart from one another. That is, again, what is referred to, as we'll see more in this chapter, an endothermic process. Energy in or absorbed. If I want to make a bond between these two things, it's actually a exothermic process. So for example, if you got two things moving around, they have to lose energy. And when they lose energy, they lose enough energy that they now can kind of come together and bond. With all their high energy, they're not going to calm down enough to really come together. So as they lose energy, they kind of slow down and then allows them to come together to kind of make that bond that's going to occur. Energy is released in this case. There is the classic potential energy. Potential energy is stored energy, or energy based on position. And we have kinetic energy, which is the energy of motion. And as I mentioned before, really the first law of thermodynamics is what is referred to as the law of conservation of energy. Energy can neither be created nor destroyed, but can transform from one place to the next. And when we think about energy sort of transferring in chemistry, we think of it as kind of like a perfect sort of transfer, if you will. So what I mean by that is, for example, we go back to our system and surroundings example. If the system loses 5 joules of energy, the surroundings will gain 5 joules of energy. It's like a perfect transfer. The energy has to end up somewhere. And again, if somebody loses a certain amount of energy, somebody else has to gain a certain amount of energy. And that's what happens, for example, in all those textbooks, right? You got the classic example of the big giant boulder on the tip of the mountain about ready to fall off, right? It has a certain amount of potential energy based on its position. And when it falls off and starts to come down, it now goes from potential energy to kinetic energy, right? And then when it hits the ground, it transfers all that energy to the ground. Hopefully nobody was underneath it when it hit, but it transfers all that energy to the ground as well. And it actually comes to rest at a different potential energy than where it started from, because it actually transferred some of that energy along the way, right? As it was moving, as it hits, it disperses that energy out as well. Any questions on that? Yeah. Yeah, so Yeah, so in the case of making and breaking bonds, the bonds themselves have a certain amount of stored energy, if you will. For example, uh, it has a certain amount of energy that you do have to kind of put in there to break it. So it would be more of like its potential energy because it's sort of energy due to its position or its sort of bonds in this case. It has a certain amount of energy. Yeah. Other questions? Now, thermodynamics, as I mentioned, is the study of energy and interconversions of energy of different kinds. And one of the things you hear a lot when you talk about sort of energy, and you also talk about it in other thermodynamic sort of properties, which we'll talk about in Chem 1B, is what's referred to as a state function. And a state function is the idea that it does not matter how you get somewhere, the path that you chose to get there. In state functions, there's really only two things that are important. Basically, where you start and where you end is basically the two important things. So for example, if you look at this little diagram here of these two hikers, they both started down here. They both ended up here. The blue hiker took the more direct route up the mountain. The red hiker here took the more scenic route around it. But in terms of their potential energy, they both have the same potential energy because they both started in the same position, they ended in the same position, and the only important thing are those two things. That is why when we calculate something, for example, like energy, pressure, volume, temperature, later on, you'll talk about entropy in 1B and so forth. These are oftentimes calculated by taking the final minus the initial sort of state. And those are really the only two important things. Now, a couple things to fill in some of the pieces. When we talk about a chemical reaction, we oftentimes talk about a chemical equation. And in a chemical equation, we have reactants that go to products. And this is always how a chemical equation is written, reactants to products. Reactants are your starting material. Products are what was formed or made. So in the case of something like energy, in the case of something like thermodynamics, very often how we calculate these things is we take the difference, we take the change of the products minus the change of the reactants. And that's what the delta here means, change. So we take the change of the products minus the change of the reactants. Again, in a chemical reaction, your final state's your products, your initial state's your reactants, where you started and where you ended. And that is why we calculate a lot of things, as we'll see in here, for example, delta H, which is the change in enthalpy, is the change of the products minus the change of the reactants. Again, final state, initial state is something, a way you could calculate energy. And in a chemical reaction, that's what we usually look at. That's also why, for example, as we'll maybe touch upon in this chapter or maybe a later chapter, but not all reactions occur, for example, in one move or one step. So not all reactions will go directly from the reactants to the product. So for example, you could have a reaction that, the first reaction is A plus B makes C plus D. Then like C plus D makes E plus F. I know my alphabet. And if you add these guys together, these guys will actually cancel, and it'll give you this overall reaction of A plus B goes to E plus F. And now there could be a certain amount of energy associated with the first reaction, and there could be a certain amount of energy associated with the second reaction. And it doesn't really matter how many steps it takes to get there. It just matters where you started and where you ended. To find the energy of this guy, you would actually just add those together. Energy of the first step plus the energy of the second step in this case. So sometimes people think in chemistry, for example, when they see a chemical reaction, they think it much as always occur in just like one move, just from here to there directly. And a lot of reactions, that's not how they occur. They actually occur in a lot of individual little reactions that when they're added together gives you really the overall reaction that's taking place. And that's the good thing about state functions is it doesn't matter if it happens in 2 steps, 4 steps, 1 step. You could figure out the energy because the only important things is where you start and where you end. Any questions on that there? So change in energy, as you see, final minus initial, pressure, final minus initial, change in volume and temperature, also state functions, final minus initial. And you should always, again, as we talked about, I think the other day somebody asked a question, definitely should always do final minus initial. Again, in some cases, if you do get a negative from something like that, like the temperature, that's really important, especially in this chapter. So I would say in this chapter for sure, just don't take the difference when you're trying to figure out the change in temperature. Make sure you always take the final minus the initial, and that will give you a negative sign if you need it, or it'll give you a positive sign if you don't need a negative. So just don't take the difference. Sometimes people are taught when it comes to temperature, just take the difference. It doesn't really matter. It does matter in terms of energy and the sign that you get. As we'll talk about, the sign that you get in terms of energy will tell you whether or not a process is exothermic or endothermic, either going to absorb energy or release energy. Okay, we're going to continue on here. Any questions on anything we've been talking about so far? All right, then let's see. Let's continue on here with our talk of energy. As I mentioned earlier, a common units of energy, definitely here, and none of these are negative, by the way. These are just PowerPoint, so I'll get rid of these kind of things here. As I mentioned before, joules and kilojoules are a very, very common unit, and here's your conversion between joules and kilojoules, which you should probably know. You'll use that probably a lot as well. As I also mentioned, they don't use it a heck of a lot around here, but sometimes they might. But again, the lowercase calories and kilocalories also common units of energy. Again, in 1 kilocalorie, there is 1,000 calories is the relationship there. Now, traditionally, this relationship's also a good one, although we don't really come across it a lot in this particular class, but when you take 1A, you will come across it, so maybe it's a good thing to kind of put in your back memory there. If you do have a joule, that is the same as a kilogram, meter squared, second squared as the units. And again, it doesn't super pop up a lot in here that I could even remember mostly, but definitely when you get into 1A and also 1B as well, that sort of conversion does pop up a lot. Now, when we talk about calories, the definition of a calorie is the amount of heat that's required to raise the temperature of 1 gram of water by 1 degree Celsius. And this conversion is a good one to know. 1 calorie is 4.184 joules. We actually will see this number a little bit later on. So that 4.184 number definitely pops up a lot. So you definitely should know that for sure. One way that we use energy is to change the temperature of a substance, for example, ice to liquid water. Now, when something gains energy, we do see a difference in temperature, right? So, for example, if we had something in degrees Celsius and something gains energy, what that does in terms of our temperature is we see a rise from the initial temperature to the final temperature and whatever is gaining that energy. So the reflection of something gaining energy is that we do see an increase in the temperature of that substance. And opposite of that is if we see something that sort of loses energy, our energy is sort of removed, what we actually see is the initial temperature, we'll actually see the temperature decrease, and we will see a decrease in the final temperature. As I mentioned last time, one of the most important things in terms of energy when you're doing calculations is really the sign that you end up with, and really where the difference in terms of whether or not you will end up with a positive energy value or a negative energy value is this change in temperature, which should again always be your final minus your initial. So for example, if we take this situation here in an endothermic process where we're gaining energy, our final temperature is actually a larger number than our initial temperature, which is a smaller number. So when you take a larger number minus a smaller number, you end up with a positive difference for the temperature. And that ultimately will usually allow you to end up with a positive value for energy. Now, if you take this situation over here and do the change in temperature, which is our final minus our initial, here our final temperature is actually smaller than our initial temperature, which is larger. So here we're taking a small number minus a larger number. That is where we're going to end up with our negative. So it is really important, again, to take that final minus initial, not just the difference, because that is where we're going to see whether or not something's going to be endothermic or exothermic by it being positive or negative, and that's going to come from that change in temperature part of the calculation. Yeah. You do. So that's one of those numbers, and that's where it comes from. And that's one of the numbers you do need to know. So that's why I said that 4.184 number we'll see a lot, and you use it a lot actually in here. Yeah. That is the specific heat capacity, as we'll talk about very shortly, of liquid water. Yeah. Other questions? Okay. Now, thermal energy, on the other hand, is the energy that's associated with the random motion of atoms and molecules. And the more vigorous the motion of the atoms, the hotter the sample will be in terms of thermal energy. And there is a difference between thermal energy and temperature. And sometimes people think thermal energy and temperature are the same thing, but there is a difference. As I just mentioned a second ago, temperature is sort of a reflection of the heat flow or energy flow, either in or out of a substance. Thermal energy is related to how many atoms or molecules are present. Now, an example of that is if we had a cup of coffee that was at 70 degrees Celsius, and we had a bathtub of water that's at 40 degrees Celsius. In terms of the thermal energy, the bathtub here actually has more thermal energy. And that's because comparison of the bathtub to your cup of coffee, we've got the large size of coffee, it's going to have way less water molecules right in your cup of coffee. So because this guy here has a lot more water molecules present, a lot more vibrations and motions, a lot more thermal energy than over here. Now you may be saying, but isn't the 70 degrees a hotter temperature than 40? And it is. It's a reflection as well of the idea of the energy required to change the temperature here. And that is something that was sort of related to what the question was a second ago. For example, water, liquid water, has what is known as a specific heat capacity of 4.184 joules per gram per degree Celsius. And what that means is you got to put in there 4.184 joules for every gram of water to see just a one temperature change. And clearly, because the cup of coffee here is way less water molecules, you could see a greater temperature change in that mass of water than you would if you heated it with this mass of water. It's going to take a lot more energy to see the temperature change. It is, as we'll talk about, one of the reasons why people get concerned when the ocean water changes like a 0.5% of a half a fraction of a degree or something like that. And you think, well, it doesn't seem like a lot, but if you think about how much water is there and how much energy is needed just to move it just that fraction of a degree, that's a lot of energy to do that. And here, because there's a lot less water, obviously in the coffee cup, we do see a bigger or higher temperature because it doesn't take as much energy to see that temperature change in that much water, as opposed to the bathtub. You could heat them both the exact same way. It's going to take a lot longer to try to get that bathtub up to 70 degrees than it would if you have a lot smaller amount of water. Same example, if you ever boiled water, which is a little bit of water in it, right? It starts to boil really quickly, right? And if you take like a big pot of water, right, to make pasta, for example, it takes a little bit longer for it to start to boil, right? Because there's just a lot more mass of water in there. It takes a lot more energy to see that temperature difference. In the case of water, to get it to 100 degrees to start for it to boil. Any questions on that there? So let's talk a little about heat and the flow of heat. Heat can be defined as the flow of energy due to a temperature difference between two objects. And heat always flows from hot to cold, right? So heat always flows hot to cold. The hot guy cools down, the cold guy warms up, and if they're in an insulated container, they'll probably meet somewhere halfway between their temperatures along the way. A exothermic process, as we've been talking about, is any process where energy is released, it is given off, and it transfers thermal energy to its surroundings. So for example, if you lit a match, you can put your hand near the match, don't touch the fire, but you can feel the heat coming off of that, right? So all that heat is coming off. You lit a Bunsen burner the other day, I imagine in a lab, and if you put your hand near it, don't touch the Bunsen burner when it's lit, but if you go near, you can feel the heat coming off into the surroundings. An endothermic process is any process where energy is absorbed by the system from the surroundings or vice versa. And again, there are two sort of ways that we represent heat and also energy in chemistry. Q is used for heat. Q is sort of the symbol for heat. And delta H, as we'll talk about, is the change in enthalpy. And that is a very common way that we represent heat and energy in reactions. The delta H, which is the change in enthalpy, is, you could think of it as really how much energy is either absorbed or released as a result of a reaction. So how much energy is sort of given off or absorbed as a result of that reaction. Now, when we talk about exothermic processes and energy, pretty much if you do a calculation, usually a negative value. So usually Q will be negative and delta H will be negative. And frankly, that's as quick as you could determine something, for example, if it's exothermic or endothermic. Very common in chemistry, they give you the delta H value and it just says negative whatever. As soon as you see that negative sign, the number is not important. The negative side tells you it's an exothermic process that's occurring. For endothermic, it's about being positive. And in an endothermic process, energy and heat values are positive values. So the delta H would be positive. The Q value would also be positive for an endothermic process. And as I mentioned, in a lot of cases, this oftentimes, especially with Q, comes down to that change in temperature. So as we just talked about a second ago, always final minus initial. So if you have a negative, you'll have the correct negative and so forth. And you shouldn't get rid of the negative usually when you're stating energy calculations. So if you have an energy calculation and it's negative, it doesn't necessarily mean it's wrong or you did something wrong, but it means that, again, that's more of an exothermic process rather than an endothermic process, which will yield you basically a positive value for those guys. So these are energy diagrams, and when we look at energy diagrams, we actually see a couple of things here. The one on the left is an exothermic reaction energy diagram, and the one on the right is an endothermic reaction. So energy is being released here. And energy is being absorbed here. And this is our reactant. So remember, in a reaction, we start with our reactants and we go to our products, right? So again, we start here and this is what we end with basically, right? So kind of final and our initial. So here's our reactants in this diagram and this is our products. And when we look at the energy associated with this, the energy of our reactants are higher than the energy of our products. So the only way for our reactants to get down to our products in terms of energy is released in this case. And again, that allows our reactants to get down to our products. If you look at the diagram on the right, which is an endothermic process, this is our reactants, this is our products. So the reactants are actually lower in energy than our products. So the only way for our reactants to get up there in terms of energy to our products you got to throw some energy in. Yeah. Energy needs to be absorbed in this case to allow those reactants to get to the products. When we do a chemical reaction, and if we didn't skip around, you would know that what happens in this case is nothing happens other than we basically break all these bonds on our reactant side, and then we make all these bonds on our product side. There is a conservation of elements in a chemical reaction. What that means is if I started with 4 carbons on the left-hand side, I will end with 4 carbons on the right-hand side. They may just be in different things on either side of the arrow, but we'll have the same number of elements. We never ever change elements as a result of a chemical reaction. Whatever we start with in terms of the elements is what we end with in terms of the elements. And they're just in different compounds on the left-hand side and the right-hand side in most cases. So what is happening as this reaction is taking place is as this reactants are starting to go through this reaction, and for a reaction to take place, basically 2 things has to happen. There has to be some type of collision between the reactant molecules. They actually have to come in contact with each other. They actually have to hit each other in the right spot. So just because they actually hit each other doesn't necessarily mean that they will actually go on and make products. They actually have to hit each other sort of in the active spot, if you will, in the right location. And secondly, they actually have to hit each other with the right amount of energy to allow products to be formed. So just because things collide, if they don't collide with the right amount of energy, if they don't collide with each other in the right location, you actually will not get products made. So not all collisions result in like products being made. You got to have those 2 things happen. So as these reactants are starting, you're starting to break some bonds, and they're immediately also in the process of making bonds. And they will continue to break and make bonds as they kind of head up the hill here to the very top. And what you have at the very top of the hill here, this is what is sometimes referred to as the transition state. The transition state, if you look at the diagram, is pretty much the highest point in energy you have in this reaction. It's really the highest point in terms of energy. Now, one of the important things in chemistry is about energy. Things do not be energy. Pretty much everything that occurs in chemistry, most of it is occurring for the whole sole purpose of just kind of bringing everybody's energy down to a lower state of energy. So low states of energy is really preferred in chemistry. High states energy is not very much preferred. It's kind of an unstable situation. And that's why when you reach this transition state, it very quickly will usually drop down to the other side because it does not want to be in that high state of energy for a very long time. At the very top of the transition state, you have what is referred to as the activated complex, our transition state complex, and this is at the very top right here, transition state complex. And what that thing is essentially something with partially broken bonds and partially made bonds, right? So you got some partially broken bonds happening. You got some partially made bonds occurring at the same time. And that's why it's called a transition state, right? It's transitioning really from the reactants into the products. And in order to do that, it has to kind of break the bonds that were originally there and allow those bonds to sort of readjust and come together on the product side to make the new products on the other side. The transition state complex doesn't hang around a very long time because, again, it's way up here at the very top. It's the highest point in energy. It just drops really quickly, usually to the other side. Now, what is this hill that is climbing? This hill that it is climbing to get to that very top point is also a really important part. This right here is what is known as the activation energy. And the activation energy is sometimes abbreviated E of A. And that is, as I was mentioning a second ago, that minimum amount of energy that is necessary for a reaction to actually occur, for products to actually be made. It's the minimum amount of energy needed for a reaction to occur. And over here, same thing's happening as it's progressing up this hill. We're breaking, we're making bonds, we're getting to our transition state. And right from here to here is its activation energy, that big hill right there. That activation energy hill is what plays a really big effect, for example, in the rate of a reaction. So if you have a really big hill to climb to get to the other side, there's probably going to be less reactant molecules that have enough energy to do that. So this reaction is probably going to proceed a lot slower than if you had a really small activation energy hill. There's going to be a greater amount of guys that have enough energy to get up and over the hill to the other side. Like if you had to walk a big giant hill to get to the other side of campus, not everybody's going to want to do that, right? You go, never mind, I don't think I want to go that way, right? But if you had to just go over like a speed bump like you have in the parking lot, right? And that's not a big hill, right? Most people could go up and over the speed bump with no problem. A lot more people will be able to make that, right, than going up the big giant mountain on the side. And that affects really the rate. So the larger the activation energy, usually the slower the reaction is because it takes you don't have as much reactive molecules that have that much energy to get to the other side as you do in a smaller one. Now, when we talked about delta H, which is our change in enthalpy, which is a super common way that energy is basically displayed in a reaction. If we look at this energy diagram here, if you take the difference between where the reactants are and the products are in terms of energy, this is the delta H for that reaction, that difference in energy. Now, if you look at an exothermic reaction, as I mentioned before, if you take your delta H for your reaction, it's the delta H of your products minus the delta H of your reactants. If you look at an exothermic, our reactants is a higher or larger number than our products in terms of energy. So because of that, our products would be a smaller number minus a larger number. That is where we're going to get a negative value here for an exothermic reaction. And that is why this guy is going to be negative because of that. And that is different if you come over here. This is where our reactants are. If I could draw a straight line. And that's where our products are. And that difference is the delta H of this reaction. And in this case, for an endothermic, if you took the delta H of the reaction, delta H of your products minus delta H of your reactants, here the products are a larger number than our smaller reactants. That's going to give you a positive value. So this is the reason why we talk about delta H. If it's negative, it's going to be exothermic. If it's positive, it's going to be endothermic. You can also see the reason for a couple of things. Which one has the greater activation energy or a hill to get to the other side? Exothermic or endothermic? Endothermic, the guy on the right, right? That's also why perhaps you need to put some energy in there to help people get enough energy to get up and over the hill to the other side, right? So that's why overall it needs some of that. On the left-hand side, much smaller hill, why it's exothermic, you got extra energy. Most things have enough energy to get up and over, and that's why we're able to release some energy. One way that you could speed up a reaction, for example, and make it occur faster if you took an energy like this here. Just do something like that here, reactants and products. And this would be our activation energy. One way you could do it is you could add what is known as a catalyst. And we'll talk about a catalyst in a number of chapters, but a catalyst is not a reactant. It's not a product. And it does not get used up in the reaction. It is there simply in most cases if you add a catalyst to speed up the chemical reaction. There are catalysts to slow it down, but most of the time people talk about catalysts in terms of speeding up the reaction. Typically where you see catalysts in chemical equations is oftentimes the catalyst is written on the arrow. So you may see something like platinum if it's a metal catalyst. You can see H plus if it's like an acid, that's a catalyst. So a lot of times on the arrow in an equation, you'll sometimes see things written, and sometimes those things are catalysts, and they're not considered reactants, they're not considered products. They actually don't get used up. They just really facilitate that reaction occurring a lot faster and a lot more efficient. So for example, let's say we had a reaction where we had gas molecules that frankly, in order for the reaction to occur, they gotta go find each other, right? So if you do not have a catalyst present, they're just flying around in hopes of coming in contact with each other, right? So what you could do sometimes is add a metal catalyst to this. And what that metal will sometimes do is, okay, the gases would actually be perhaps attracted to the metal. And by doing so, what that's going to do now is put those gas molecules a lot closer to each other, a lot more efficiently, right? They're going to be able to come in contact with each other a lot faster. That's going to allow them to collide and get the reaction going in a much faster and efficient way. Ultimately, the way a catalyst makes a reaction occur faster is what it affects on this diagram is it actually affects the activation energy. It lowers the activation energy, a catalyst. And what that means is now instead of these guys having to go way up here, these guys just need to get up this smaller hill to get to the other side. And what that's going to do is allow more reactant molecules enough energy to get up and over to the other side a lot quicker. And that will speed up the rate of the reaction typically. So catalyst finds an alternative pathway, a more efficient pathway for the reaction to occur, lowering that activation energy, allowing more reactant molecules to get to their side. The end result of that is usually the reaction will speed up. It's like the old cartoons where the roadrunner like opens the trap door and goes through the mountain, right? Closes it, and the coyote's got to go up and over to the other side. So finds just that alternative pathway. Any questions on that there? So again here, energy, this reaction is exothermic. Our reactants are higher in energy than our products. So again, energy is going to be given off in this case. Delta H for this guy would be a negative value. This is decomposition of mercury 2 oxide. That is our reactants going to our products. Again, in this case, energy needs to be absorbed. Delta H would be a positive value in this particular case. So I would say 9 times out of 10 in a chemistry problem, if you had to make, for example, you're given an equation, you have to make like a determination, is it like exothermic or endothermic? Most commonly, the way that's displayed to you is like this. They'll give you the equation, and next to the equation, they'll go, hey, this is negative 125 kilojoules for the delta H. And again, here, the number really doesn't matter. It is that negative sign that will tell you this reaction is exothermic. So that is a very, very common way that exothermic and endothermic sort of display to you in chemical equations. Any questions on that there? All right, so exothermic, again, energy is released. What does that mean for the actual equation? I would say in our class here, and probably 1A and so forth, you probably don't see too much of this, where they will sometimes actually write into the actual equation an energy value. So here we see 213 kilojoules, that's an energy value. And we see it on the product side. And we consider exothermic reactions that energy is considered a product, which will be on the right-hand side of the arrow, like it's being given off, basically. So we see energy on the right-hand side. So if you're ever asked to kind of write the energy value into the actual equation, you should see it on the right-hand side. And if you do see it on the right-hand side, it indicates that it's exothermic and is considered a product. We'll actually see this in one example, maybe at the very, very end of the semester. You'll see it more in 1B when we talk about Le Chatelier's principle. And one of the ideas there is in exothermic, we consider energy as being a product. So sometimes in exothermic reactions, energy is kind of considered like a product. And that is opposite over here when we see the energy in the reactant side. That is considered an endothermic reaction, like it's being absorbed. So if you see any type of energy value written in on the reactant side, you should think of it as an endothermic process. If you see it on the product side, you should think of it as an exothermic process. And again, you probably won't see energy too much written like that in this class or the next class. Um, but that is sort of what we think about exothermic and endothermic in terms of reactant side of the equation or product side. Any questions on that there? So as I mentioned before, what's going to happen when we have some type of insulated container, we got a hot water and cold water situation. Remember, again, heat is going to transfer from the hot to the cold. So it's going to transfer that energy over to the cold water. The result of that is all these water molecules over here are going to gain a lot more energy. The result of that is the temperature on the right-hand side should start to increase. The water on the left-hand side is going to lose all that energy, which means all those water molecules are going to slow down, and the temperature on the left-hand side is going to start to decrease, right? So we're going to see a lot more motion happening there on the right-hand side, a lot less motion happening there on the left as it starts to do that. And eventually, if this is sort of an insulated container, they'll kind of come to rest at what is known as equilibrium. They'll come to the same temperature, basically. Both sides will come to that same temperature. It is the same idea as we'll talk about if you took some water that was, say, room temperature-ish, and you took a hot piece of metal that's like 99 degrees Celsius, and you throw that metal into the water. The heat is going to flow from the water to the metal or the metal to the water in this case? Yeah, because the metal's 99 degrees and the water's 25 degrees, the metal's way hotter, right? So the metal's going to release all that energy into the water's temperature, right? The result of that, again, is what we're going to see is the water's temperature is going to start to increase, right? Because it's gaining all that energy from the metal. The metal's temperature will start to decrease, right? Because it's releasing all that energy into the water. Eventually, the metal will come to rest at what temperature? The same temperature as the water ends up at, right? Because it's now sitting in there, right? It comes to equilibrate with the temperature of the water in that particular case. Now, opposite is true, right? For example, if you took your 25 degrees Celsius and you took your metal out of the freezer and it was minus 3 degrees Celsius, when that goes in, which way is the energy going? In this case, your room temperature water, even though it's not super cold or super hot, is actually hotter than the metal. So all the energy from the water is going to actually go into your metal, right? The metal's temperature in this case will actually increase, right? And the temperature of the water will actually decrease, right? This situation over here for the metal, is it exothermic or endothermic? On the right. The metal is exothermic, right? It's releasing all that energy. For the water, it is endothermic. It's picking up all that energy. Opposites over here. For the water over here, it is exothermic, right? And for the metal, it is endothermic, right? So it's picking it up. So again, remember the flow of heat and energy, kind of like a perfect transfer, right? So whatever energy the metal releases here, is all the energy the water is going to gain, right? And whatever energy the water releases here is all the energy that the metal will absorb. So again, you want to kind of think of it as almost like a perfect transfer of that energy from one object to the next. Any questions on that there? So let's talk a little about enthalpy. And like I said, probably in chemistry, enthalpy is the most common sort of unit. And enthalpy is used to express the heat released or absorbed during a chemical reaction. The change in enthalpy will give you that idea if it's exothermic or endothermic. Again, if you got a positive value, endothermic, negative value, exothermic. How do we calculate the change in enthalpy if all you have is the actual equation? We do our really final state minus our initial state, as I've been talking about, and that is our products minus our reactants. Where can you find this? There is usually a table known as the delta H of F, delta H of formation, that you can look up in a book are a table in the back of your book that gives you a bunch of values for anything that's there. So for example, let's just say we have this equation here, 2a plus 3b goes to 4d plus e in this case, right? And let's just say that if I look up on this table here, A, B, D, and E, and they have them delta H values here. We'll just make up some numbers here. Let's go with negative 125. These are going to be kilojoules per mole. We'll go minus 62. We'll go plus 38. And we'll go minus 46. We'll see how we do here. So if we wanted to calculate the delta H for this reaction, we would go to this table, or obviously the values would be provided for you, and we would take the delta H of our reaction would equal our delta H of our products minus the delta H of our reactants. Now, when we look at the coefficients in a balanced equation like this, these numbers 2, 3, 4, and if there is nothing written there, it is a 1. Yeah, so usually 1s aren't written in chemistry, so it is a 1. These are what are referred to as the moles of each of these. So there's 2 moles of A, 3 moles of B, 4 moles of D, and 1 mole of E. And that mole is the same mole that is over here in this sort of unit here. And remember, a mole abbreviation is MOL, is the abbreviation for a mole. And that means that when we do this calculation, we actually have to take into account the coefficient in the equation. So for example, we would start with our product side here. And there are 4 D's. So I need to go 4 times the value I would find in the table for D. And this would be 38 kilojoules per mole. I'm going to add it to my other reactant, which is 1 times the value of E, which is negative 46 kilojoules per mole. And again, the 4 and the 1 there are moles, so that's really where the moles kind of cancel out. This is all my products. So I'm basically going to add up all the delta H's I could find from the table for my products. And then I'm going to subtract it from my reactants. I'm going to go underneath so I don't run into my table there. We're going to subtract it from all of our reactants. We're going to do the same side. There are 2 A's. So we're going to take 2 times the value of A from the table, which is minus 125 kilojoules per mole. We're going to add it to our other reactant, which there are 3 of them, times the value of B from my table, negative 62 kilojoules per mole. And I'm going to take all my reactants. So remember, state function, products minus reactants, final state minus initial state is what we're doing here. So if I do all that on the product side, that's 4 times 38 plus 1 times negative 46. And that's going to give me, I'll come up here, delta H of my reaction. Give me a 106 kilojoules minus my reactant side, which is 2 times negative 125 plus 3 times negative 62. That's going to give me a negative 436 kilojoules. That means when I do that, 106 minus a negative 436, that is going to give me a delta H for this reaction of 542 kilojoules. Not too bad. Is this made up reaction I just did exothermic or endothermic? It is endothermic because the delta H is positive. This would be in a table. It's typically in most textbooks, like in the back of the book, there's usually a table, or online, there's usually like a table. They'll say like thermodynamic values or something like that, or delta H is typically, you wouldn't have to obviously memorize it, would be provided for you. But there's usually a table that you could look these values up in. And it's really important when you go to the table, a couple of things is you want to always make sure when you look it up in the table that you find whatever you're looking for in the correct state. So if that thing is a solid, you want to make sure you look up the solid. If it's aqueous, AQ, you want to look up the liquid or gas version. I would say water is a very common one people mess up on when they go to a table. They just grab the first water they see, and it may not be liquid water. It may be like steam or gas or ice, which is solid. So you do want to make sure you look up in the correct state. Do you have a question, sir? Yeah, so that kilojoules is an energy unit. Yeah, so delta H is an energy value, and it will have units typically of kilojoules is usually what the units associated with. Per mole. Yeah. Technically, yeah, so technically speaking, the moles part actually cancels out with these numbers. These numbers are actually moles. So technically when you do that multiplication, technically speaking, those guys kind of go away. Although a lot of times people don't write the moles with the numbers, where it has the four and all that, they don't really write it. But that technically is what these numbers in front represent. That's why I said these represent the moles of each of these. So when you grab it from the table, basically what we're saying when we look at, for example, D, we don't just have 1 mole of D, which would be 38 kilojoules, right? We actually have 4 moles of it. So we need the energy that's associated with 4 moles of those. And that's why we have to multiply it by the coefficient. But I will say sometimes people will still leave the moles at the end of the calculation as kilojoules per mole. But I'm usually good with just kilojoules if you come across it. But technically speaking, that's sort of where the moles part cancels out at that point. Yeah. G means gas. So when you look at a formula for something, there'll usually be like a little parentheses next to it a lot of times. And it'll either have one of these 4 symbols. It usually will have either S, L, G, or AQ. S means solid when you see it. L means liquid. G means gas. And AQ means aqueous. It's basically a solution. And a solution is really a homogeneous mixture, like we just talked about in the last chapter. So, like the salt water, when I wrote that formula, if you remember, I wrote NaCl and I put AQ next to it. It indicates it's a solution, which is a mixture, and that's a homogeneous type mixture. So usually what the difference, and sometimes people are confused by these two guys here. What is the difference? The difference is a liquid is a pure substance by itself. So if you just had water, that is a pure liquid. There's nothing else with it. It's just H2O, nothing else mixed with it. But when you take water, like we did there, and we're talking about a mixture, and you mix it with some sodium chloride, with those two things together, you now get aqueous, which is a mixture and a solution. They're both in the liquid state, but one has something dissolved in something else. So typically something that's aqueous usually means that you took something like solid and you dissolved it in something like water to make a solution. While something that has just the L next to it is just one pure substance by itself, nothing else in it. Other questions on that? All right, so let's see here. Perfect. Why don't we try one here? Why don't you give it a go? So these are some real values that you would find in a table. So why don't you calculate the delta H of this reaction and determine is it endothermic or exothermic? See what you come up with here. Values you can find as we talked about in one of those tables. As you can see with real stuff here, again, you can see the different states you want to make sure you find. This is also something that you'll commonly see with delta H's. And if you look at sodium by itself or H2, anything really from the periodic table, for example, and H2, as we talked about earlier, that is how it naturally comes as a diatomic molecule, right? As H2 or hydrogen gas. Any element that's pretty much not combined with anything else will typically have a delta H value of 0. So 0 is very common what you find for anything that is basically by itself, not combined with anything else, anything from the periodic table, how it naturally comes. Usually the value is 0 for it. Again, here we're going to calculate our delta H by taking our products minus our reactants. So again, we do want to take our coefficients. So we're going to start on our product side, which is over here. So we have a 2 there for our sodium hydroxide. We'll take 2 times the value, minus 470 kilojoules per mole. We're going to add it to our other guy, which is H2, and there's only one there. And basically that's going to be 1 times 0 here, kilojoules per mole. And that will take care of all of our products, right? So if we had 3 products by some chance, you would just add the third guy in there. We're then going to subtract it from all of our reactants, which is over here. So we have 2 times our value for sodium, which is 0, plus our other reactant, which is 2. And again, this is water in the liquid state, so we do want to make sure we get the right number there, and we do need to take it 2 times the minus 286 kilojoules per mole there. And this is all of our reactants. Any questions on the setup there? All right, so if we do this, we're going to take 2 times minus 470, and that's essentially going to give us a negative 940 kilojoules, minus on the right-hand side there, basically 2 times negative 286, going to give us a negative 572 kilojoules. So minus 940 minus a minus 572, going to get us a negative, I think, 368 kilojoules in this case. Any questions on the calculation? Endothermic or exothermic? It is exothermic, and that is all you need to worry about right there is the negative sign. So overall, this reaction, when it takes place, will give off about whatever I had there, 368 kilojoules of energy will be released to the surroundings as a result of this reaction taking place. Any questions on that there? All right, let's try another one here. Okay, let's take a look again. Pretty much, by the way, if you're just given a reaction, you're asked to calculate the delta H of the reaction. Pretty much head to that table is pretty much the right approach. So once again, we're going to take our products minus our reactants in this case. So we'll start over here on our product side. We have 12 CO2s, so 12 times the value of CO2 from the table there, minus 393.5. We're then going to add it to 6 times our value for water, which is 286 there, negative. And once again, that is going to pretty much take care of all of our products, or really our final state as we've been talking about, minus our initial state over here, which is our reactants. So we'll do our 2 times our 4904. And we're going to add it to 15 times the O2, but since that is something in its standard state, as you can see there, it is a 0, which is what you will find. And this is going to take care of all of our initial state, which is our reactants. So once again, here we're going to do our addition and multiplication. So 12 times negative 393.5 plus 6 times negative 286. That's going to give us something like a negative 6438 kilojoules on the left there, minus 2 times 4904, basically. And that's going to give us 9808 in this case. So negative 6438 minus a 9808 looks like a negative 6536 kilojoules in this particular case. And once again here, this is going to be exothermic, right? Any questions on how to calculate delta H from just the equation? So clearly, obviously, the equations should be balanced. If they're not, you do need to make sure they're balanced. And what that means is, you need to make sure you have the same number of carbons on each side. That's 12 carbons, 12 carbons, 12 hydrogens, 12 hydrogens, 24 and 6 is a lot there. 30 oxygens on each side. I would say for our purposes, it should be balanced because we haven't talked about the balancing chapter yet, but just in case maybe a homework problem or something like that, it does need to kind of have the same numbers on each side. Yeah. Yeah, although I wasn't truly paying a lot of attention, but this guy's a whole number there, and we would be adding, so we would technically take this guy to whole number like we did there, and then over here on this side, technically the way they wrote it, this was a whole number, this should be a whole number, so probably they both, when you subtract overall, should end up as a whole number. Yeah. Other questions on how to calculate delta H? Okay. I would say probably for our applications, you should know how to do this calculation, but most of the time the way we're going to kind of see delta H is to help us determine exothermic or endothermic. But if you did need to calculate, obviously this is the way that, one of the ways you can calculate and the way that you should calculate it. All right, so again here, this is a combustion reaction like what you do when you light your Bunsen burner. And it is an exothermic process releasing that amount of energy. Again, we know that because our reactants are higher in energy than our products, resulting in the energy being in and off. And as we saw, if we do a phase change here, take solid ice in this case, which is our reactants, to liquid water, which is our products. Again, that is an endothermic process. Our products are higher in energy than our reactants. And you think about that, right? That's what happens with an ice cube, as we talked about, right? When you take that ice cube out of the freezer and you put it in room temperature, the room temperature, right, is a hotter temperature than the ice cube. So the heat from the surrounding air is going to flow into the ice cube. And that's why we see the ice cube just start to melt spontaneously, right? Just by itself with no help needed. By the way, the flow of energy, we can't see that. I was waiting for him to come in again. The flow of energy, as we can see that, for example, when we're doing an experiment, right? What would happen if I'm holding a test tube, which is not a great idea in a lot of cases, but if I'm holding a test tube and test tube gets really hot, the reaction in the test tube is endothermic or exothermic? It is exothermic, right? Because your hand is now absorbing all the heat and energy, which is why it gets hot, right? If I hold the test tube and it gets cold, yeah, it's sucking all the heat and energy out of your hand, which is why you get cold, right? It's how the hot like pads, right, and hot cold packs work, right? You break it, does a chemical reaction, you're holding onto it. It's an endothermic chemical reaction, gonna suck all the energy out of your hand, right? That's why it feels cold. And obviously, if you have a hot pack and you do it, right, it's gonna release that energy into your hand, and that is why you feel hot. Also, again, why when you're like, for example, have water on your body, right? You feel cold. But you get out of the pool, right? You have a lot of water in your body. Water in your body is going to be colder than the heat from your body. Heat from your body is going to evaporate, right? The water, that's an endothermic process. All the heat's going to come from your body, which is why you feel really cold, right? Also, why you feel really sweaty, right? That's why we do sweat as well, right? We sweat because when we get perspiration on our body, it increases the evaporation rate, right? And cools us down and releases the energy from our body and it cools us down as well. When you're in a really steam, like you've ever been in a steam room or a sauna or something like that, right? There's a lot of heat in there, right? There's a lot of condensation occurring because the outside temperature is hotter than you. And when it hits you, right, it starts to go through condensation. And that's why also when I take a hot shower, the mirror gets, right, all watered up basically, right? Because all that hot steam hits the cold mirror, right? And it goes through condensation when you do that. So let's talk a little bit about specific heat and how to calculate specific heat, which again is another way that we look at energy. Again, none of these are negatives, just from PowerPoint there. The specific heat capacity of a object or a substance is the amount of energy that's required to raise 1 gram of that substance by 1 degree Celsius. And there is an equation that we use. Q is equal to ms delta T. Q here is the heat, and it usually has units of either joules or calories. M is the mass, and it has units of grams. S is the specific heat capacity. And it has units of joules per gram per degree Celsius or calories. per gram per degree Celsius. That is the definition, by the way, of specific heat. It is the energy, joules, required to raise 1 gram of a substance by 1 degree Celsius. That is why you have 3 units. That is the definition, basically, of specific heat, is all 3 of those units there. Super confused most of the time. Q and S, people always go backwards on that. So Q, which is heat, should have just 1 unit. The S there, which is specific heat capacity, should have 3. And then obviously here, as we've been talking about, our change in temperature going to be our final minus our initial. This is probably one of the only equations that you'll come across in chemistry where you actually do leave the temperature in Celsius. So very often we convert things to Kelvin. This is one of the few times that you actually would leave it in Celsius. And that's because the specific heat capacity that we deal with is usually in Celsius. And as was an earlier question, this is the one that you should definitely know. Yeah, so this is the specific heat capacity of liquid water. 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. Remember, that is your conversion factor between those two. 1 calorie is 4.184 joules. So again, this is where you sometimes will convert between those two. Now, sometimes people will use, instead of the S, sometimes people will use the C to represent specific heat capacity. Some books will use SH to represent specific heat capacity. I personally go with S, but some books do use C nowadays instead of S. But it represents basically the same thing here. It's the specific heat capacity of a substance. The higher the specific heat capacity, the more energy you need to put in there to change the temperature of that substance by 1 degree Celsius. So if I have something like water, which has a very high specific heat capacity of 4.184 joules per gram per degree Celsius, as I mentioned earlier, you got to put in there 4.184 joules of energy for every gram of water that you have to see 1 degree temperature change. If I had a specific heat capacity for something else that was like 0.25, that would mean I only need to put 0.25 joules of energy in there to see 1 degree Celsius change in 1 gram of that substance, so much less energy. So the lower the specific heat capacity, the higher energy change you'll see versus something with a higher specific heat capacity. It takes a lot more energy to see that temperature change. Q, as I mentioned before, if it is negative, exothermic. And Q is positive, endothermic. And as we talked about a number of times today, when you look at the specific heat equation, this guy here is always going to be positive. The specific heat capacity is going to be positive. So once again, it is that change in temperature, as we talked about earlier, that's going to really determine whether or not you're going to get a negative value for Q or a positive value for Q. If you do Q, by the way, at constant pressure, that also will equal the delta H. You're kind of calculating almost a delta H value. So at constant pressure, you could very simply calculate the delta H value by calculating Q. Now, how do you do this? You need really fancy scientific type of equipment to do this. Honestly, you could do this in what is sometimes referred to as a coffee cup calorimeter. Couple foam, styrofoam cups, basically, stacked together with some water in there, and a lid and a thermometer. And frankly, you could do all the reactions in those coffee cups and just use the thermometer to find the change in temperature that's occurring. And you can find the amount of energy that's either released or absorbed as a result of that chemical reaction. Because we know the specific heat capacity of water, and as we talked about before, even reagents that are not water, which are aqueous, which means it's basically water-based. We could even do it with things like hydrochloric acid, which is water-based, sodium hydroxide, which is water-based, and all we have to use is specific heat capacity. I'll spit that out. The specific heat capacity of water there, even though we're using something like HCl and sodium hydroxide. Here's a table from your book. Again, you can also see that if you're dealing with ice, which is the solid version of water, it has a very different specific heat capacity. It's actually 2.03. If you're dealing with gas, it is 2. And obviously here, and that is the same as our 1 calorie per gram per degree Celsius, the specific heat of liquid water. So again, obviously need to know that guy. But keep in mind, sometimes people always kind of use the 4.184 in all situations with water. But if you're dealing with ice or steam, you do need to use more of a 2 value there for your specific heat capacity. So why don't you try one here? Determine the amount of energy as heat that's required. Okay, so let's take a look. And a good idea, like I mentioned perhaps before, is just kind of pull out the information to help you maybe figure out maybe what you need to do. So we're looking for the heat. So we know Q is heat. To raise 10 grams, that is a mass. We have a specific heat capacity of 0.89 joules per gram per degree Celsius. And we have an initial temperature of 25 degrees Celsius and a final temperature here of 58 degrees Celsius. So definitely you can kind of see the specific heat equation hopefully staring at you in this case. In this case, we do have everything on the right-hand side, so we can just plug in. So we got 10 grams. We have our specific heat capacity, 0.89 joules per gram per degree Celsius. And again, we want to go final minus initial, so 58 minus 25 degrees Celsius. Here, the grams are going to cancel. The degrees Celsius is going to cancel. That's going to leave us with joules, which is good since we're looking for energy. So that's going to get us here 10 times 0.89 times 58 minus 25 there. It's going to get us on our calculator here 293.7 joules. Technically speaking, if we're sig figging it up here, that is 3 sig figs, right? And that is 2 sig figs. We are subtracting here, which means we're going to a whole number since they are both whole numbers. I believe that's 33 when you do that, which is 2 significant figures. That means my answer most likely should be 2 significant figures, right? And smallest, since we're multiplying, so maybe like a 290 joules would be good. And if you use that, we are looking for calories as well. So 1 calorie, 4.184 joules. So we'll go 290 joules. 4.184 joules is 1 calorie. Eh, And if you use the rounded number here, you will get 69 calories. If you use sort of the non-rounded number on your calculator, you get about 70 calories, I think. You did the non-rounded version there and did the conversion. Any questions on that? The answer to your question is I probably would take either, but 69 would be good. I'm sorry, was that your question? For here? Mhm. Right. Yeah. So we're doing a couple of different things here, right? We're doing in this part of it, we're doing subtraction, which means we should be looking at decimal places. And each of those numbers are whole numbers, which means when we subtract it, we should take it to a whole number, which was 33, which would be 2 significant figures. Now that we have that number that actually is whole number and 2 significant figures, we're then going to turn our head to really the last type of calculation we did, which is multiply it all the way across. And at that point, we're going to look at sig figs, and I think we had 3, 2, and technically 2 sig figs here that came from subtracting to the whole number. Yeah, you're welcome. Yeah. I would probably take it. Truthfully, I'll be honest, I'll give you 2 answers to that, which maybe is not a good thing. Technically speaking, since we're looking for both of these answers, you probably should round this guy to 290, and then that would get you here. Personally, if I was doing it, I probably would have still took like I did on my calculator, and probably divide it out and get to the 70. So I would have done both. Yes, sir. All right, let's try another one here. 294 joules of heat is transferred to 10-gram sample of silver at 25 degrees. What is the final temperature of the silver? Specific heat capacity of silver is 0.24 joules per gram per degree Celsius. All right, so let's take a look. Again, we're going to pull out the information. So we got 294 joules. Again, remember, it is Q that has the 1 unit value. Yeah, so not is not S, so that is Q. We have our mass, which is 10 grams. We have our initial temperature here, which is 25 degrees Celsius. We're looking for the final temperature in this case, and we do have S, which is our specific heat capacity. And again, this is the one that has all 3 units. And I can't tell you how many times people do confuse Q and S and kind of get them backwards. So at this point, we can use our specific heat equation. Q is equal to ms delta T. We do have Q, we have M, we have S. We don't have all the stuff we need, obviously, for change in temperature. As we know, our change in temperature is our final minus our initial. So we do have this. We are looking for this. So we want to first perhaps solve for the change in temperature so that we can eventually get to our final temperature, which is in that. So I'm going to rearrange this. A reminder that if you need to rearrange an equation, we're basically multiplying everything on this side. So to get things to the other side, you do the opposite, which means we need to divide the M and the S to the other side so that they cancel. So opposites always get things to the other side. So delta T would equal QMS in this case, which is everything that we have. So we'll put our numbers in. 294 joules, our mass of 10 grams, and our specific heat capacity 0.24 joules per gram per degree Celsius. And if we do all this good stuff here, 294 divided by 10, I'm going to hit equals and divide it by 0.24 and hit equals. This is going to give me a change in temperature of 122.5. The units are degrees Celsius, as the joules will cancel. The grams will cancel. When you divide this, the degrees Celsius will go to the top, right? Here at this point, this again is not our answer, right? That represents the change in temperature, which is essentially this guy here. So we just got what was in the box there. At this point, we know that change in temperature is equal to our final minus our initial. Again, we're subtracting here, which means opposite to bring it to the other side. We need to add, and that's going to give us a final temperature. That is the change in temperature plus the initial temperature. I personally am not going to round at this point. Otherwise, you know, we kind of get far away from maybe the true value here. I am going to think about where I should be, though. Just based off of this calculation I just did previously, we're dividing and multiplying. This has 3 sig figs, right? This guy has 3 sig figs. And this guy has 2 sig figs, which means technically speaking, that is about where I should be. Yes, sir. Why do we move this to their side and add it? Is that what you're asking? Yeah, it's because you basically do opposites when you move across the equal sign. So here, this number is being subtracted. So to get rid of it, we need to actually add it to the other side. Yeah. Yeah, because basically, for example, say we had like x minus 5 equals whatever on the other side, and we wanted to move it to the other side, we actually have to add 5 to both sides. And when we do that, minus 5 and plus 5 basically go away. They equal 0. Yeah, so we got to do it. It's always opposite, and that's why we divide it over here at the beginning, because basically we're taking m times s times delta t. So we're multiplying. If I want to move it to the other side, do the opposite function, which is divide. Yeah. So always opposite function as you move it to the other side. Yeah. You could also, if you're multiplying, just go in opposite location. And it's in the other side. Yep. Other questions on that? All right, so here, again, I'm not going to round. So I'm going to take the 122.5. I'm going to add it to my 25, which was my initial. And that is going to get me here a 147.5 degrees Celsius. technically speaking, this number should have been 120 if we started, which is a whole number added to a whole number, which means this guy should actually end up here in the very last multiplication, or very last math step that I did was adding. So probably 148 degrees Celsius would be the appropriate answer in this particular case. So really it is the last step that you do that kind of determines where you end, but you do have to take in all the previous steps into consideration as you kind of move through it. And again here, if I would have rounded a little bit here and went with the 120, I am going to get a fairly significant difference. You know, I'm going to be about 3 degrees difference, right? Which is kind of a big difference. So here, because I want to kind of give that as my final answer, I'm not going to round at that step there, but I am going to keep track of it, which tells me it should have really been 120, which is a whole number. And the last thing I did was add, which is 2 whole numbers were added together basically. And we should end up at a whole number. Yes, sir. It has, it's based off of the last thing that we did, which is adding, and we look at decimal places at this point. We look at decimal places, not significant figures. Yeah, so if we add or subtract, we look at decimal places. So this is a whole number, and this is basically, you can look at it either as really what it should be, which is a whole number, or as one decimal place, but it should be there. And that's different than what we did up here. Up here, we were multiplying, dividing. So here, we were looking at sig figs when we were doing that. Okay? And that's how we got really, if we were going to give our answer for the change in temperature, we really should have took it to 120 at that point, would have been the proper one if we were stopping the calculation at that point. Yeah. Other questions? Okay. So let's talk a little about a very common specific heat situation that occurs, which is the heat transferring from one object to the next. And we sort of talked about it a second ago when we were talking about the energy transfer. But let's just say, for example, we did have a glass of water or a beaker of water here. And let's just say we had about 115 grams of the water. Let's say the initial temperature of the water was 25 degrees Celsius. And let's say we took a piece of metal here and we had a mass of the metal of 95.5 grams. We had an initial temperature. We heated that thing to like 90. Actually, let's do 99.0 degrees Celsius. And let's say we took the piece of metal and we dropped it into our water in this particular case. And when we do that, the final temperature of the water, let's just say gets up to like 27.5 degrees Celsius. Now, a couple things going to happen here, right? We're going to get a transfer of energy. And in this particular case, the energy is going to transfer which way? From the metal to the water or the water to the metal? The metal to the water, right? The metal is 99 degrees, right? The water is 25 degrees. So the metal is much hotter than the water. So the energy is going to be released from the metal. As we talked about, that means it's going to be exothermic for the metal. The water is going to be endothermic. What's going to happen to that piece of metal if it just sits in that water? Eventually it will come to what temperature? Will come to the same temperature as the water, right? Since it's sitting in there. So it'll actually come to the exact same temperature at this point. Now, what is the other thing that we know about the water? We know the specific heat capacity of liquid water is 4.184 joules per gram per degree Celsius. So let's just say we wanted to know for the metal, what is the specific heat capacity of the metal in this case? We could actually use all the information for the water to help us figure out what's happening with the metal. So if we do our Q for our water, it will equal ms delta T, which we have all of that information. So if we do that, my mass is 115 grams. My specific heat capacity of my liquid water, 4.184. Final temperature minus initial temperature. Guess we'll see how bad I did here. So here we got 115 times 4.184 times 27.5 minus 25. And that's going to give me 1202.9 joules, as the grams will cancel, the degrees Celsius will cancel. Technically speaking, at this point, sig fig wise, I have 3 sig figs. I have 4 sig figs, and technically here 2 sig figs. Again, we're subtracting, which means we go to decimal places. They both have 1 decimal place, which means we should go to 1 decimal place here, which would give us 2.5, which is 1 decimal place and 2 significant figures. So technically speaking, this number should end right about there. I am not done with my calculation at this point, so I am not going to round like normal, but I am going to kind of keep track of kind of where I should be. First off, any questions on that? Now, all that energy that was absorbed by the water, it is endothermic, right? Because we have a positive value for Q, for the water. All that energy that was absorbed by the water came from what thing? All came from the metal. Now, we talked about the transfer of energy, right? It's kind of like this nice perfect transfer, which means if the water gained 1202 joules of energy, how much energy did the metal lose? It lost the exact same amount of energy, right? The only difference is it is exothermic for the metal, which means the metal should actually have a negative value for that. And this relationship is Q of the metal is equal to negative Q of the water. So in this case, negative 1202.9 joules means that my Q for my metal should be negative 1202.9 joules. The exact same amount of energy that was gained by the water should be the exact same number that was lost by the metal. The only difference is the sign. And again, this is what I was talking about earlier. Sign, really important with energy. The sign on the metal tells us that is going to be released by the metal. The sign on the water is that's how much was absorbed, right? The amount of energy is the same value, but the sign is different. Any questions on that? Now, how did that help us for our metal? If we do our Q equation for the metal, ms delta T, we now have Q of the metal. We now have our mass. We have our change in temperature. That is going to allow us now, by just simply following the change in temperature of the water, we can now figure out something about the metal. Opposites again, we're multiplying here, which means both of these guys are going to be divided to the other side. And that will give us S is equal to Q of the metal divided by M delta T. If I put my value in there, that's negative 1202.9 joules. The mass of my metal is 95.5 grams. And now for the temperature change of my metal, what is my final temperature? Again, it is the smaller number, right? 27.5 minus 99 degrees Celsius. Why is doing it this way really important here? What type of number am I going to get when I do that? A negative number along with this negative number will turn my specific heat capacity into a positive number, which is what you need. So again, you got to do that final minus the initial for the negative sign here to make sure everything cancels out correctly. So getting our number in this case, and we got this. We end up with this number here, 0.176165196. None of these units cancel, so it's joules per gram per degree Celsius, which are the proper units for specific heat capacity, right? All 3 of those. By the way, now we need to figure out sig figs, right? So clearly we know here, we should have ended up here, which technically is 2 significant figures, right? Down here, this guy is 3 significant figures. And when I take 27.5 minus 99.0, I get 71.5 degrees Celsius, which is 3 significant figures, which means my answer really should be how many significant figures? 2. which is based off of the original calculation we did up here. So again, that's why it's important to keep track of that all the way through. We should end up with 0.18 joules per gram per degree Celsius, which would be the specific heat capacity of this metal. Again, super simple to do. You just need a thermometer and some water, and you can basically figure this stuff out. Super simple with some coffee cups. Yeah. If you have multiplication and division, you follow the rules basically of how you would do the math problem, basically. So for example, if we come back to the here, we would typically do things in parentheses first. So technically, we would do that subtraction first at the last point here. And at that point, the subtraction part should be looking at decimal places. And each has one decimal place, which means the answer is 71.5 is the proper answer for just that part of the calculation. And that has one decimal place, but it also has three significant figures. So now the last thing we do is taking this number and multiply it by this number, and this number gets divided by both of them. And at that point, we switch from decimal places now into the very last calculation we're doing, which is multiplying and dividing. It is. It's really the last calculation that kind of determines where you end up. But if you have multiple calculations along the way, you got to keep track of what those numbers should be when they reach the last calculation that you do. Like here, I had to keep track of this top number. This top number is not five significant figures. It really should only be two. And that was based off of the previous calculation we did. So you have to kind of keep track. And that's why sometimes people will put these little lines over it just to remind you, hey, this is where this number should end. And they will sometimes do it that way. But you got to kind of keep track of it through the entire calculation. The last one ultimately determines where you end up. It does, yeah. So that's why, and that's why also you really shouldn't round too early because